I am making this video to get us a satisfying proof of the formula for the surface area of a sphere. So the way that we get the overall surface area of a solid like this starts out just as a line segment, and then that we end up rotating that line around, in this case, the x-axis. So let's imagine what's happening at each point that we then rotate around the x-axis. Each point here creates a circle that represents the path that point takes around the x-axis, and that generates a length. And so the way that we actually get surface area is by taking the summation, the infinite summation, aka the integral, of each of those individual lengths. And you can see that each of those lengths is a circumference of a circle. And so yes, each of those individual circles that we created gets added up and forms the overall surface area. So if we have a length and then times dx, that's a length times a length, which is an area. So let's look at how we would construct this guy. So what we would like is to have the circumference of each of the circles that gets created. So we're going to go the integral from a to b. So the surface area is equal to the integral from a to b. And again, it's the circumference, so it's 2 pi r, where r is the height of the function. So it's f of x. And then from there, what we're going to want to do is, it's not just enough actually to integrate from a to b. We want to integrate along the length of this line, right? So we want to keep going up and up. So that is what we call ds for the length of the line. But ds can be further expressed as, if we zoom in to what's happening along the length of that line, we have a little tiny triangle here. And so the hypotenuse is delta x squared plus delta y squared and the square root of that. And then in order for us to be able to ultimately integrate in terms of dx, what we can do is pull out this delta x squared from the square root. And again, when we're doing this approximation towards an integral, the delta x is really dx. So if we pull that delta x squared or dx squared out of this square root symbol, then we can get that there. As long as we then divide the inside of this square root, both of those terms, also by delta x squared. So delta x squared over delta x squared is 1, and then delta y squared over delta x squared, aka dy dx squared, or dy dx squared. There you go. So this is the or is that then this also could be considered f prime of x. So if we have the derivative of the function at each point, and for the case of a straight line, this derivative would be a constant, but for a curve, which we can get into, that will simply be the derivative at the individual x values. So this is a comprehensive formula there for this or for any curve. So what we're interested in right now is applying this to a sphere and how we can get ultimately the formula for the surface area of a sphere, which we know is 4 pi r squared. So what are we actually rotating? In this case, we are rotating a semicircle around the x-axis. And it doesn't matter in this case what the radius is, because we ultimately want this to be a general formula. So if the radius is half of this distance, then we can call this 2r. Cool. And then we can give y in terms of x, or f of x. The formula for a semicircle, the overall, it's x squared plus y squared equals r squared, but we just have the top half of this guy. That's when it's centered around the origin. So here's what it's going to be. Y equals, it's going to be the positive, this is x minus h squared, where h is the x coordinate of the center. So that means that we're going to transform this into y squared equals r squared minus x minus h squared. And in this case, h is also r. And so then when we do y equals, we take the square root of both sides. So we have r squared minus, if we expand this, x squared minus 2xr. Then we can simplify. So we have r squared minus r squared, so those cancel. So we have negative x squared plus 2xr as what we're taking our square root of. So that's our y equals our f of x. And so from there, what we can do is take the derivative in order that we can plug it into our formula. But this is what we are going to put into f of x. And okay, f prime of x, we have 1/2 of negative x squared xr to the negative 1/2 times the derivative of the inside, negative 2x plus 2r. Boom. And so let's plug that into what we have. So integral from 0 to 2r, we can bring the 2 pi out front, and then our f of x we have as, I'll just put it in terms of 1/2, so negative x squared plus 2xr to the 1/2 times 1 plus all this, 1/2 negative x squared plus 2xr to the negative 1/2 times negative 2x plus 2r. Great, and dx at last. I just realized that I did not square my derivative. So this is f prime of x here, but I did not square it, which actually is okay because it's going to make this a little bit easier. So by squaring this, here are the only things that change. This 1/2 becomes a 1/4. This thing gets squared, and then this gets squared, which means it actually does cancel with the multiplication of this. So we have 1/4 and then negative 2 plus 2r parentheses squared. Great. And so now we can do some simplification. So negative x squared plus 2xr. And we can expand this. So 1/4. And in fact, there's a 2 common here that is getting squared. So that is a factor of 4. So that cancels. So basically what we're saying is that it's just going to, what we're squaring is negative x plus r. This turns into that. So that is x squared minus 2xr plus r squared. And again, square rooting this whole thing. These x squareds now cancel. The 2xr's cancel. Oh my gosh. So now we have the square root of r squared dx. Crazy. 2 pi 0 to 2r. Square root of r squared is just r dx. And so we're going to now take the antiderivative, 2 pi, and this is going to be r times x, again from 0 to 2r, of plugging that in for x. So 2 pi r times 2r minus 0. This is our plugging in for x, and that gives us 4 pi r squared. We did it. Whoop, whoop. I hope that was satisfying. I know we went on a journey here. This ultimately originates from the arc length formula, proving the arc length of a given line, combining it with the neat fact that when we do rotate a line or a more general curve, we get this 2 pi r circumference happening, so 2 pi times the individual f of x. And then I also realized that could have made this even simpler by doing potentially have this semicircle centered around the y-axis. I guess all it really would have done is it would make it negative r to r instead of 0 to 2r. It's amazing that a lot of stuff actually does in fact cancel out the square roots and such. So this, just to be clear, would be like a -1. And then when we multiply it together, again, those cancel out. So yeah, there's your 4 pi r squared. Ta-da!